Hello and welcome back. Let's practice our tabular integration on example 5. What's going to be our choice for u? If you said x cubed, that would be correct. That would make your dv the sine 2x, all the rest of the function inside the integral. Again, x cubed was a good choice because by Liate, the a for algebraic function, which is what the x cubed is representing here, comes before the t, which is the trig function. So we'll want to definitely let u equal x cubed. That'll be a good choice for you, and for me too. All right, now that we've got our u chosen, we're going to go ahead and take derivatives all the way down. Let's keep taking derivatives until we get to 0. 3x squared, 6x, 6, and then 0. With polynomials, you can do that. You can keep taking derivatives until they eventually go down to 0. Now, with other functions, you may not be able to do that. And in that case, you might have to pull out of integration by parts, or this repeated integration by parts. And that's okay to do too. And I'll show you how you can do that in example 6. But here, we were able to go all the way down to 0 because u was a polynomial. Now, on the right side, we're going to have to integrate sine 2x. It's a little bit tricky because we have that 2x there. But if we think, okay, we have the integral of sine is negative cosine. We just have to remember that there's going to be a factor of a half in front to cancel off the effect of the chain rule if we were to go back and take the derivative, right? There's this extra 2 that we need to cancel off because of the chain rule. Or if you wanted to, you could do a u substitution and let u equal 2x. That would be like the previous packet 20's technique. But that's a little bit overkill for here. Let's just think about integrating sine 2x, and you're going to get negative 1/2 cosine 2x. You can always double check by taking the derivative and making sure that you get back to sine 2x. Let's integrate again. So integral of cosine will be sine. We're still going to have that 2x in front of there, but again, we're going to have an extra factor of a half out in front. So the 1/2 times 1/2 will give you 1/4. Double check it by taking the derivative of negative 1/4 sine 2x and making sure that you get negative 1/2 cosine 2x. What would be the integral of negative 1/4 sine 2x? What would you get there? If you said 1/8 cosine 2x, that would be correct. Remember that the integral of sine is negative cosine, so we have an extra negative that makes the coefficient now positive. It flips the negative of the negative to make a positive. And we also have an extra factor of a half that pops out in front. And then what about the integral of 1/8 cosine 2x? If you said 1/16 sine 2x, that would be correct. So we have all of our u derivatives, all of the dv integrals going down until our last row here. We stop it when we get to that 0 row. So now we're going to write out all of the uv's that pop out. The uv's, remember, are on our diagonals. And the sign of the first uv will have no sign flip, so it'll just be like whatever the sign of uv is, that'll be what it is. The next uv is going to have its sign flipped. The next uv will not have its sign flipped, and the next uv will have its sign flipped. It always starts off positive, negative, positive, negative. Now we can write out what the integral is, because now we know what all those uv's are. The first uv is going to be x cubed times negative 1/2 cosine 2x, and that one won't have a sign flip, so it's just going to be negative 1/2 x cubed cosine x. Let me switch to skinny font because it's going to be a lot going on here. Negative 1/2 x cubed cosine 2x. Now the next uv here, we've got 3x squared times negative 1/4 sine 2x, and we're going to flip that sign. So it's like a negative 1 times a negative 1/4 is 1/4. So we'll have plus 1/4 x squared. Oh, whoops, I'm sorry, plus 3/4. We have that 3 times negative 1 times negative 1/4. That's 3/4. And then sine 2x. Now we're going to have 6 times 1/8 and no sign flip. That'll be 6/8, which is 3/4. Then for our variables, we have x times cosine 2x. And then for the last UV, we've got 6 times 1/16, which is 3/8. And it's going to be negative, so minus 3/8 sine 2x. And don't forget our plus c. Whew. That would have taken a lot of work if we had written out all those u's and dv's and the equals and the dx's and everything. So this is a much more streamlined way of doing that. Let's look at example 6, which is a good example that comes up many times. So we have the integral of e to the x cosine x dx. Let's start by doing integration by parts. And if you think about doing integration by parts, well, by Lyautey, trig function would come before exponential function, so we could let u equal cosine x. But it turns out that both of those functions, when you take derivatives, just keep going back, back to the same thing. So like derivative of e to the x is e to the x, and derivative of cosine x is negative sine x, but then the derivative of negative sine x leads you back to cosine x. It's negative cosine x. So you just keep cycling back and forth. So all this is to say that trig functions and exponential functions are equally bad. So it doesn't matter if you let u equal e to the x or u equal cosine x. Either one is going to be equally bad. I'm going to go ahead and just let u equal e to the x for our integration by parts. And I'm going to write that off to the side. You let u equal e to the x. Let the dv be cosine x. So the te part of Lyautey they're both equally bad. So you can let u equal either t or e, doesn't matter. Now let's take one step of integration by parts. Here we're going to take derivative of e to the x, which is e to the x. The integral of cosine x would be sine x. Now thinking about if we pull out of integration by parts right here, we're going to get e to the x sine x minus the integral of sine x e to the x. Right? This last row here is what goes inside of your new integral. This is like your v du. Sine x is like your v, e to the x is like your du. We're just not writing the v's and the du's, but they're you can imagine that they're there. So if our new integral is e to the x sine x, it doesn't look like that's really that much simpler than the old integral of e to the x cosine x. We're still kind of stuck in terms of integrating. So let's go ahead and try doing one more integration by parts. We're going to do one more integration by parts where we let u equal e to the x and dv equal sine x. So we're just going to make one more row in our tabular integration. Derivative of e to the x is e to the x. The integral of sine x is negative cosine x. And something interesting will happen here. If we try to figure out what our new integral would look like after we do this integration by parts, well, the bottom row tells us what's going to be in our new integral. It'll be an e to the x cosine x. And that's interesting because that's exactly what we started with. We started with an integral of e to the x cosine x. Let's try to pull out of integration by parts here. We're going to pull out of doing this tabular method and see what we have so far. So the way we can pull out is like this. These diagonals are still the UVs that are popping out. They still alternate positive, negative in terms of the sign flip or no sign flip. But this last row, we're going to pull out and write that last row inside of an integral. And that one is going to have a positive sign in front of that. It alternates signs. That sign in front of the integral would be the sign in front of the new uv, which would be positive. So let's write what we have. We have e to the x sine x. That's the first uv, e to the x sine x. Then we have e to the x times cosine x. And for the signs, we have a negative and a negative, which makes a positive. So plus e to the x cosine x. Then for the signs, we have positive, negative, so that's minus the integral, because remember this row right here is in the integral. This is the v du inside of our integral. and then we have e to the x cosine x dx. Now what we're looking at here is the integral of e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x minus the integral of e to the x cosine x dx. We have the thing that we're looking for, which is this integral of e to the x cosine x, on both sides of the equation. Let's try to solve for it by getting rid of it on the right side and bringing it over to the left side. We can do that by adding the integral of e to the x cosine x to both sides. That integral is some kind of quantity, and so we can just add that quantity to both sides. So on the left side, we're going to get 2 of those integrals of e to the x cosine x dx. And on the right side, we've got e to the x sine x plus e to the x cosine x. Now if we're trying to solve for this integral of e to the x cosine x dx, all we have to do is divide the 2 over, and we'll be done. Oops, I forgot an x there. We'll get e to the x sine x plus e to the x cosine x over 2. And then because we have an integral like this and we want to write the general antiderivative, we're going to put our plus c at the end. And that's it. That's how we can handle one of these integrals that cycles like this. When we do integration by parts twice, we end up cycling back to the original integral. And that ends up being a good thing, because then on the next step we can bring those integrals together, those unknowns that we're looking for together, and then we'll have some coefficient. We can divide by that coefficient. The coefficient won't always be 2. It depends on what other coefficients you have going around here. One thing I should mention is that sometimes textbooks will replace the integral here with a letter like I, and so you'll end up with something that looks like I equals e to the x. Probably shouldn't draw that line there. E to the x sine x plus e to the x cosine x minus I. So trying to abstract this integral as just some variable that you can mess around with and move around to one side of the equation and another. So maybe I should just write or. So this I is representing that integral that we're looking for, the integral of e to the x cosine x dx. Then what you can do is add the I to both sides, just like we did. So add the integral to both sides. I stands for integral, by the way, in case you were wondering. Left you hanging in suspense there, I know. So you get 2i equals e to the x sine x plus e to the x cosine x. And then you can divide the 2 over. So I'll just put dot 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 here. It's exactly like this. So the I is like this variable that you're trying to solve for, but again, it represents this integral that you're trying to solve for. So one last thing I wanted to mention is a note of caution. Caution. Maybe it deserves an exclamation point. A really common mistake that I see, so I'll put a not equal to. A really common mistake that I often see is when people are just learning how to integrate. The mistake is wishful thinking, which is thinking that maybe the integral applies separately to each of these factors, separately to the e to the x and separately to the cosine x. And so some people might do like this. Integral of e to the x is e to the x. The integral of cosine x is sine x. And maybe I'm done. But you can quickly realize why that's not going to work. It's not going to work because derivatives don't work that way. You can't take the derivative separately factor by factor. You have to use the product rule to take the derivative of the product of two functions. So if you were to turn around and check by taking the derivative of e to the x sine x, you wouldn't get e to the x cosine x. You can't take derivatives term by term or factor by factor. You can't individually take the derivative of e to the x and the derivative of sine x. Instead, you have to use the product rule, in which case you would get two terms. You would end up getting, let me write this out. you would get first times derivative of second plus the derivative of the first times the second. And this is not matching what you get in what you have inside that integral. These two are not equal. So our check completely failed. So you definitely do not want to make this mistake. If there were a plus in the middle, if there were a plus between the e to the x and the cosine x, then you could write this. That's equal to e to the x plus sine x. But without that plus, you can't integrate factor by factor. So thankfully we have this integration by parts method to help us out here, because if we didn't, it would be very difficult to do this problem. Thanks again so much for watching, and see you next time.